All right, here's a problem that we've just introduced, the concept of shear force and bending moment, and we want to find these values. So actually I forgot where I wanted to find these values. Let's do it at point C. Okay? So I'm going to cut the structure here at point C. Now, which side do you want to work? The left side or the right side? Left side or right side? Right. Okay, if we do the left side, what do I have to find? Reactions. If I do the right side, do I have to find any reactions? No. That could be an advantage. So I'm going to take advantage of that advantage by cutting it at C and looking at the right side. Now, if I do that, you'll notice at C there is an applied force there. Can you cut it underneath that force? Not really. But I can cut it just to the left of that force and get as close as I possibly can, infinitesimally close. And then I can cut it again just past the force on the right side. And we'll do that. We'll do it twice and see what difference it makes to the bending moment and how it affects the shear force. Okay? So the first thing I'll do is we'll look at point C, is where we're trying to find this thing. And I'll say just to the left. So you can imagine that you're going through the structure and you stop just on the left side. So my free body diagram will look something like this. There's the body. Now, since I'm stopping just to the left, then that 500-pound force is at C. Then I have another one at about midpoint. And another one at the end. And let's not forget our applied moment out here of 2 kips per foot. And I'll just go ahead and pencil in my dimensions. Now at this cut surface, I'm going to assume positive shear force, axial force, and bending moment. So here's my positive axial force. And again, I'm using that little superscript of the plus sign to remind you that that's the positive. Then I'm going to have positive shear force and positive bending moment. Everybody see that? Okay, at this point now I'm just going to do equilibrium. So I'm going to assume that this structure is in equilibrium. So I'm going to start by summing my moments at the cut that I just made, making sure it's in equilibrium. I'm using right-hand rule for my sign convention. So let's start here at the left side. What kind of moment is this when I'm summing moments with this sign convention? Positive or negative? It's negative. So that's the thing I'm looking for, moment. And then all these 500-pound forces create what kind of moment about the cut? Positive or negative? Negative. Now this 500-pound force is so close to C that it has really no moment arm, so it creates no moment. So I'll come over here and change this into kips. So those 500-pound forces are really half a kip. And I'll have one at 10 feet moment arm and one at a 20-foot moment arm. So that should account for the moment of this force at 10 feet and this force at 20-foot distance from the cut. Then what is this? Positive or negative moment? Negative. So that'll be minus 2 kip feet. So I should be able to solve for my moment. Let's see, that's 30. Half of 30 is 15. Minus 2, this should be minus 17 kip feet. So what does that mean? I assume positive bending moment. So my bending moment at C is negative 17. So it's a negative bending moment. What is? Remember, negative bending moment, we have that analogy about happy and sad. So you expect C to be a sad face here? I do. Because if you think about the way this is going to bend, it will probably bend something like that. And you see that's kind of part of a frown. Right. I know it's not very scientific to say it that way, but it seems to be working because you're all either smiling or frowning. I don't know if that has anything to do with the problem or not. But. So I think that's good. That kind of seems like it matches our intuition. All right, let's go ahead and finish the problem. I'll sum forces now, and I'll assume up is positive, and make sure that's in equilibrium. So I look at all my forces. My shear force is up, and then I have 1, 2, 3 forces acting down. And I'll write those in kips. So that's a half, and a half. So I should be able to solve for my shear force, and it turns out to be 1.5 kips. Positive. So that means that the shear at this point is positive. And you can probably already see this one, but I'll just go ahead and do it anyway. If we do sum forces in the x direction, assuming right is positive, I only have one force. It'd be minus the axial force. But it's what? 0. It doesn't really matter its direction. So far, so good? All right, now let's see what happens as I go back to point C. And this time I go just to the right. But what happens? Well, the geometry of my free body diagram does not even look any different. But I've moved just to the right of C, so now this 500-pound force that was just to the right is now off the body. So it's not there anymore. But I still have the one about midpoint. I still have the one at the end. I still have my 2 kip foot applied load. My geometry is the same, 10 feet, 10 feet. And I'm going to make the same assumptions I did before. Axial force, positive. Shear force, positive. Bending moment, positive. So what do? Make sure it's in equilibrium. So let's do that again. So I'm going to now sum my moments about that cut again. Make sure it's in equilibrium. Let's start again. So just like our previous equation, when I'm using right-hand rule for my moments, this is a negative moment. And now I just have 2 500-pound forces. This one didn't create moment anyway, right? Had no moment arm. So it looks like they're going to be about the same. So I've that 2 kip force. The first one has a moment arm of 10. The second one has a moment arm of 20. Then they have the applied moment at the end, minus 2 kip feet. If you do the calculation, again it looks like the moment is 17 kip feet. So it seems that the moment from the left side of an applied force to the right side of that applied force doesn't make any effect in the moment. Doesn't have an instantaneous effect on the moment. What about the shear? Well, let's find out. Let's sum forces in the y direction and see what we get. So the shear force is acting up, and then I have 2 500-pound forces acting down. So what's the shear here? It's 1 kip. Uh-oh. Well, I shouldn't say uh-oh. That sounds like something bad happened. Something just happened. So on the left side of this force, I found the shear was positive 1.5. And just as I passed the 500-pound force on the right-hand side, I found the shear was 1. What's the amount the shear changed? The change in shear was what? Yeah, it actually went down half a kip, right? And what is the force applied there? It's acting down, and it's half a kip. So we're going to hold that in your mind, and we'll come back and use that. So it looks like the shear is going to change instantaneously as you go from the left side of a force to the right side of a force. And we can use that to our advantage later on. So if I were to plot this, for example, if you plotted the moment as a function of x, and let's say I'm dealing with just what's happening here at point C. Well, I know at point C the value is 17 kip feet. Now I don't know what it's going to look like, but whatever the moment diagram looks like, when it gets there and it leaves, it could change slope, but it's not going to change value. It's not going to have a discontinuity in the value. However, if you look at shear force as you move along the beam, again at that point C that we're interested about, well, what happens there? Well, it looks like the shear force is coming in on the left side at 1.5 kips and leaving on the right side at 1 kip. So it has an instantaneous change, and that's that delta that we saw before. So as we move forward and move towards doing shear force and bending moment diagrams and understanding how shear force and bending moment behave over the element, we'll know that every time we go by a concentrated force, we're going to have this step change in our shear diagram. And probably an associated change in the moment diagram, but only in the shape of the curve, not the value.
Could you explain the shape of the curve again?
Why it's these values here?
Yeah.
I just made some numbers up. I'm just off the top of my head. It doesn't really matter what they are now.
Okay.
The thing to notice is that it can change slope, but it can't change value at C. The value at C does not jump.
Okay.
But the shear does. So if I ask you what's the value of the shear at C, what are you going to tell me? I don't know. On the left side it's 1.5, and on the right side it's 1. Which one would be more critical to deal with? The 1.5. So if you had to deal with stress or any kind of secondary effect, you're going to look at locally, you'll look at the larger of the two values. Does it matter whether it's positive shear or negative shear? It does to you in terms of getting the answer right, but in terms of the effect on the structure, no. Positive and negative bending moment behave, we bend the curve differently, or the beam differently. So depending on your material, that can be an issue. If you're doing reinforced concrete, right, concrete can't handle tension, so you always want to reinforce the tension side. That could be the top of the beam or the bottom of the beam, depending on the moment. So any other questions about this? All right.